Okay. Let's see, stop sharing that. Okay, now we are ready to go here. I was just answering some questions. Let's see. Share screen. All right. So, where were we here? We got our chapter 4 homework due tonight, experiment 3 due tomorrow, and exam 1 next week. So exam 1 actually covers chapters 1 through 4. I think I was talking about it last time as if it covers chapters 1 through 5. It does not. It covers chapters 1 through 4. So we do have an exam coming up next week due on Wednesday. By Monday at the very latest, you would need to tell me where you're going to take the exam, what proctor you'll use, and that can be a proctor with one of our campuses, or it can be any professional educator, librarian, teacher, administrator, and I would need their name and their work email so that I can send them instructions. Anybody have any questions about that? Next week, we will start chapter 5, and we have some experiments due next week as well. And chapter.
Okay, I thought.
Sorry, go ahead.
Sorry, I thought last time we met, you said it was going to be the exam was going to be the week after this next one coming up.
Yeah, that's what that's what I'm telling you. I'm telling you that was actually a mistake. The exam actually covers chapter. I was thinking of my other class because I'm teaching at the same time another physics class for non-engineers and scientists. So they're essentially people that are going into like the medical fields or biology or something. And they actually have a test coming up that's chapters 1 through 5. And I somehow got it in my brain that this one was for chapters 1 through 5. But when I went and looked at our schedule, actually exam 1 covers chapters 1 through 4, and it just has to do with the way the book is organized. So we will be doing an exam after chapter 4, which would be now, right? So next week is the exam, and I apologize for that. That's my fault. If we need to extend the exam due date into later in the week or something because of that, then I'm fine with that. But we do want to get it done as soon as possible so that you're not there's not too much time between chapter 4 and the exam, so that you're not forgetting things. And like I said, I do apologize for that. That was just I misspoke from confusion. But yeah. So anyway, if you can get me your proctor information as soon as possible, I will get that information out. And then exam 1 will cover things from chapters 1 through 4. Now, the way that I create these exams is I literally go into the homework assignments and take problems from those homework assignments. And so the problems that you will see on the exam will be problems you have seen before. They will not have the same parameters in the problems. It will give you different numbers, different situation essentially, but you will have done the problems before. So the best way to study for the exam is to study the homework, go through your homework, see which ones you maybe struggled with, and practice those questions a few times at the very least. So that is where we are at. I also will make a recommendation to you as far as the open book portion of the exam. The exam is open book, and you can use your online book if you'd want. But I would recommend that you also, in addition to your online book that you might open on your computer during the exam, I would recommend that you pick a couple of pages to print off from the book, at least one. And I would print a page that has a lot of equations on it that you might use. There are pages in the book that have like all the kinematic equations on one page, and those would be useful for this exam. And then once you've printed that off, then you can add other equations or formulas to it that you might use. And that is a perfectly valid use of the open book policy in this class. It's a good thing. It's a good thing to have a page of equations and formulas all in one place so that you don't have to go searching through the book to find it. I think that you'll still find that having the book will be useful every once in a while. You might want to look something up that that will help you to solve a problem or something, but having formulas and equations in one place, certainly useful. So, any other questions involving the first exam? Okay, well, in our textbook, we have covered all of chapter 4. So today, being the day that chapter 4 homework is due, I believe, we want to answer any questions that you might have and work on any problems with the homework that you might have or any of the subjects. Once we are done answering questions from the homework, we will entertain questions about the previous chapters for the exam coming up. But does anybody have any questions from the homework? Okay. Go ahead and ask your questions. Which problem is it?
Question number 2 starting off.
Question number 2.
I feel like it's missing one part, one simple understanding to get the answer.
Okay, a bullet is shot at 298 meters per second straight left from a helicopter at a height of 612 meters. So it accelerates towards the earth. How come this isn't working? Oh. There we go. If it accelerates towards the earth for the whole fall, assuming no air resistance, it will take this amount of time. So you're going to calculate the time. Also, the bullet it will land at. Also, the bullet will land at some distance horizontal. Okay. So this is a classic two-dimensional problem, done quite often. Remember that the horizontal and vertical movement are independent of each other, right? So they don't. So it's not going to affect each other. They're not going to affect each other. But you will be able to use information from the X direction in the Y direction and vice versa. So that's useful. Whenever I'm doing a problem like this, I always split it into 2 parts, the X part, and I literally write it like this, and the Y part. I make spaces for them both. And then I draw, you're going to draw your picture. So you get your helicopter. Draw it however you want. There's my helicopter. And the bullet is going to shot straight left. Oops, I drew this helicopter. It doesn't matter. They're gonna go this way. They're gonna fire this thing this way, but I'm gonna say I'm gonna shoot it right. It doesn't really matter one way or the other. But they're gonna shoot theirs left. I'm gonna shoot mine right. And this bullet is gonna go this way from the helicopter. And its original velocity is going to be equal to 298 meters per second, and that would be in the in their version of it going left. That would be negative 298 if we assume this is the positive direction. So if we assume this is positive x direction and up is the positive y direction, which most people would, then this would be, ours would be positive, but theirs would be negative because they're going to go left. Doesn't really matter one way or the other. This is the I hat direction, so that would be my vector. We also know that once the bullet is released, it's not going to speed up in the x direction at all, because once it's out of the gun, there's nothing pushing on it anymore. So this is the velocity in the x direction at the beginning and at the end. This is the initial velocity, and the final velocity in the x direction is also equal to this. That's not the final velocity overall, just the final velocity in the x direction. So we can write down here, we can actually write some things. We can say that the initial velocity in the x direction is equal to whatever it is, whatever your number is, in this case 298. And we can also say that the final velocity is equal to the initial velocity in the x direction. So it's the same number. In the y direction, what is our initial velocity? 0, because we're shooting the bullet in the horizontal direction. So as soon as it comes out of the gun, it hasn't started falling yet, and it's just sitting still in the y direction. So our initial velocity in the y direction is actually 0. And you can see that in this vector, there is no y component, so there's 0 velocity in the y direction. And our final velocity in the y direction, which we're just going to call Vy, not V final y, but just Vy, is unknown. We don't know what that is. We also can choose our initial position in the x direction. We can choose the initial position to be 0. This is just some number up here. We can choose our initial position x0 in the x direction to be 0. But we have to make a choice about the initial position for the y, because we know the height. We know the height is 612 meters. So do you want to choose the ground to be 0, or do you want to choose where we are flying to be 0? So we're going to choose the ground to be 0. That'll be y. That means that'll be y final, because that's where the bullet's going to end up, right? So y final will be 0, but y initial, y0, will actually be 612. Now, if we'd chosen the ground, if we'd chosen the helicopter to be 0 height, then the ground would be negative 612 in height, because that's going downward, right? So our final would be negative 612 if we chose our initial to be 0 at the helicopter. But
On our question 2, our initial velocity and height are different.
Yep.
Our initial is 284 and our height is 526.
Yeah, so it doesn't really matter what numbers you put in here.
Okay.
So it'll work anyway. So your y initial is just some number, and whatever number they give you, you plug in there, right? But
Okay.
the ideas are all still the same here. And let's see if there's anything else that they've told us that we should write down. I don't think there is. The only thing else in here that we know is true is the acceleration in the y direction is equal to negative g. The acceleration in the x direction, of course, is equal to 0. We already talked about that. And that's implied in this statement here, where the velocity doesn't change in the x direction. So that's all the stuff they've told us. Here's a nice little drawing of it. We can include a trajectory of the boat. We kind of know that it's going to fall downward like that, so we can include that if we want to. But we've got everything all set up and ready to go. And this is something that you should do for every problem in physics. You should write down all the stuff that you know. You should make a drawing or a sketch or some kind of diagram to represent it, because it will help you to organize your thoughts. And while you're doing this, you will find your mind is already thinking how to solve it, right? So how do we solve a problem like this? The way that we solve a problem like this is we look at the things we're trying to solve for. In this case, we're trying to solve for time. And we're also trying to solve for the distance in x. And we're going to look for a formula or an equation or multiple equations, it might take more than one, that will give us those things using the things that we have with us already. Right? And it turns out that there is an equation that will give us the time that it takes for something to move through a known distance. We know the distance that it's moving in y. If we know the initial velocity and the distance and the acceleration, there is an equation that will tell us the time. And the equation that will tell us that is the kinematic equation that is quadratic. I believe that's the only one that will do this. So the kinematic equation that's quadratic looks like this. It's y final equals y initial plus initial velocity in y times time plus 1/2 times the acceleration. But our acceleration is negative g. We can write it in there like that. 1/2 times negative g, and then times the time squared. And I think this is the only one that will do this. I'm thinking through, and you don't want to just think in your head what equations to look for. You want to actually go look at the equations. So you would go back and you look at the kinematic equations, and we can go ahead and do that really quick. Go to our book, look at the kinematic equations, which are for projectile motion, section 4.3. And we go down here and we say, oh, here are the kinematic equations. This is the kinematic equation in x, and these are all the kinematic equations in y. And the only one that has t in it and other things that we know and everything else we know, the only one that is that way is this one here, this third equation. That's the only one that has t in it and everything else we know, so we can solve for t. So this is that equation, and we're going to go ahead and use this equation. The problem with using this equation to do this problem is that it is quadratic. So you're going to plug in a bunch of numbers, and you're going to end up with a t squared, right? Luckily, we have it easy. In this particular situation, when we plug in all of our numbers, we plug in our final y. Our final y is 0. We plug in our initial y. Our initial y is 612 or some number, whatever it is for your problem. When we plug in our initial velocity in y, it's 0. And then we end up with minus 1/2 g, which is 9.8 t squared. Well, this is really nice because this term right here that has 0 times t becomes 0, and we end up with something that is very simple to solve. We end up with something that looks like 1/2 times 9.8 t squared equals some number when we solve this. And then we multiply both sides by 2, we divide by both sides by 9.8, and then we take a square root and we solve for the time. That's simple, right? Once you have that time, that of course is your first answer, but you can use that time in another formula to calculate the distance that this thing has traveled. And that formula is also in the projectile motion section. But I'll leave it for you to find it and to use it. Does anybody have any further questions on that, or any questions about what I did here or anything like that?
I do have a question on number 3,
Okay,
but
there are no
I
more
guess-
questions for this one. We will clear it and move to number 3. So what's your question about number 3?
finding time in the air, because I did figure out the horizontal and vertical components. Actually, how does yours?
So once you found the vertical and horizontal components of the velocity, what you've got at that point is you have a ball
Mhm.
that has a velocity that looks like this. The vector for this velocity looks like v equals v sub x I hat plus v sub y j hat. Do you agree with that?
Yeah.
And if you split it into 2 parts, x and y, like this, then and this is the initial velocity, right?
No, actually, that's like
The
that's
velocity of 23. Yeah, so,
that's like. Oh, is it initial?
yeah,
it
this
is
is the
initial.
initial velocity because you calculated it from this number up here, right?
Yeah.
So your initial velocity in the x direction is equal to your velocity that they give here times the cosine of your angle theta, right?
Yep.
And same thing for y.
But that's with sine instead.
Yeah, it's using sine and the y, and so then you're good to go there. But with this here, initial velocity in the x direction, how are you going to figure out the time that it's in the air? Turns out that you can't really do it for the x direction, but for the y direction you can. This one here, you have the initial velocity, v times sine theta.
Mhm.
But you also know the acceleration. The acceleration in the y direction with projectile motion is negative g. And there is an equation that will tell you the time in the air if you know the final position. Your initial position in the y direction is we can call 0. So y0 can equal 0, but we also know the final position because it says right here that it lands at the same height. So our final position is also 0. So, and there is an equation that will tell you the time that it's in the air if you know the acceleration in y, the initial velocity in y, and the final and initial position. It's actually the same equation from the previous problem. The same equation from the previous problem will give you this answer. So it looks like this: y final, y initial equals y initial plus v naught y times t plus 1/2 g times t squared. Now the difference between the previous problem and this problem is that your v naught y is not 0 this time. So this over here gives you some number. This gives you some answer, some number that you're going to use. And you're going to actually have to plug that in to this equation. Now, in this equation, you actually do have initial position and final position equals 0, which is nice.
Mhm.
Because that's actually going to make this answer work out. So you're going to end up with 0 here and 0 here plus some number, which is your initial velocity in the y direction times t minus 1/2 gt squared, right?
And I'm guessing G would be 9.8.
Yeah, G is 9.8 there.
Okay.
And when you solve this, you're going to get a term that has t in it and a term that has t squared in it and no constant terms. And that means that you're going to be able to factor out a t from the equation and then just solve for t directly. So that actually makes that one pretty straightforward as well.
Give me a second. Let me try that. So 7.69. Let's see. So for factoring out t, that would mean I would have to square root what I got from, like, okay, so if,
So let's actually do this really quick, do these steps really quick. So going from here, you're going to end up with a number times t
mhm,
minus 1/2 times 9.8 times.
yep, times t squared.
When you factor out the t, and this is equal to 0 because there's nothing over here.
No,
When you factor out t, you're going to divide both of these by t, and that's going to go away, and this is going to go away here. And so you're going to end up with a number minus 1/2 times 9.8 times t. And if you add this to both sides and then multiply by 2, divide by 9.8, you'll get your answer. So the next step would look like this. I'm going to go up here to do the next step. The next step, I'm going to add this term to both sides, and I'm going to get the number times t equals 1/2 9.8 times t squared. Then I'm going to factor out the t so that I just have a t on one side and no t on the other side, just the number. And then I'm going to multiply by 2 on both sides to get rid of the half. That's going to go away there. And I'm going to get 2 times my number on this side. And then I'm going to divide by 9.8 on both sides to get that. That's going to go away there. And that will equal t. So your time ends up being 2 times your initial velocity in the y direction, because that's what this number is. So you're
Divided by
9.8.
Okay.
So it ends up being 2 times v sine theta over 9.8. And this is how all of these problems will go.
All right.
Every one of these problems goes like this. You have some things that they tell you, they just tell you explicitly. Then they have some things that they imply that you have to figure out, like the ball starts and lands at the same height. So then you have to say, well, I'm going to call my initial height 0. If it lands at the same height, that's also 0. So you write those things down. You write down everything that they tell you and everything that you can infer from the problem. And then you calculate anything you can calculate. If you can calculate your initial velocity in the x and your initial velocity in the y from the stuff that they give you, then you go ahead and do that. And you put it into a separate x and y sides. And then you can use the kinematic equations. You go through the kinematic equations and you find one that will give you something that you need using the things that you have. And maybe that will be on the x side of things, maybe it'll be on the y side of things, maybe it'll be on both. You might end up using multiple equations. You might end up using one equation on each side, multiple equations on each side, only one equation on one side, 2 equations on one side. You know, there's any number of combinations of things that you might have to do to end up solving the problem, but you're really just looking for an equation that will work to get you the thing that you want using the things that you have. It's kind of like taking, you know, those complicated word problems that they gave you in trigonometry and algebra to the next level, to a whole new level of, you have to find your equation now. You have to, you know, maybe use multiple equations. And that's really the reason that we put you through college algebra and trigonometry, is to prepare you for this kind of thing. So if you just tested out of those and took classes like them in high school, then it's essentially the same education, even if you didn't actually take the ones that are called those things. If you took a couple of algebra classes in high school and a pre-calculus course or something, then you've got the same stuff, hopefully, in your brain. So
I'm still a little confused by numbers. Those are plug into there once we get to that point.
which numbers we plug into this equation down here?
The two, and these
This?
Yeah.
Oh, the V is right here. It's the velocity that they gave you right here.
and it's three.
And the theta is the angle. And I should have labeled those. Usually I will label them. I'll actually write it in here. I'm calling this theta and I'm calling this V. Right? I didn't do that. I apologize, but usually I would do that. I just heard an interview with Elon Musk the other day. Somebody was interviewing him about his success. And, Elon Musk didn't finish college. And everybody is just amazed that he is the richest person on earth. And not only the richest person on earth, but he's accomplished some amazing things. When nobody knew who Elon Musk was, when his only real accomplishment was PayPal. If you've ever used PayPal, you can thank Elon Musk because he came up with that idea as well. But back then, hardly anybody knew who he was. And somebody went to a party where they met him and they asked him, so what are you doing these days? You've done PayPal, what are you doing these days? And he says, right now I'm thinking of a way to build a rocket that will take us to Mars. And the guy laughed at him. He laughed at him out loud and said, I think you had better work on something that's more achievable. And here we are. Elon Musk is building a rocket. He's not only designed one, he's actually building it and he's tested it and it has actually flown. It hasn't left orbit yet, but he has tested a rocket and a capsule, not a capsule, but an actual spaceship that will actually be eventually going to Mars. It's undeniable at this point that it's going to happen. And when they interviewed him about his success and accomplishments, one of the questions they asked was, what would you tell people to study to be successful? What is the one thing that you would tell people to study if they want to be successful? And he didn't even hesitate. He said, physics. He was a physics major in college and he didn't finish college. He got most of the way through it. But he said that the most important thing for anyone to study, it doesn't matter what they're trying to accomplish. It doesn't matter what they're trying to do. But if they want to be successful, he said the number one thing to study for success in general, no matter what you want to do with your life, is physics. And they said, physics? Why? It's such a specialized thing. Only scientists and engineers use it. And he said, that's absolutely wrong. Physics, especially at the beginning of physics, the first couple of years of physics, is mostly just about problem solving, learning how to solve critical problems using tools that you have available to you. And that's what we're doing here, is we're giving you some tools, we're giving you some understanding, and then we're saying, let's solve some problems. Let's figure out what we know in the problem. Let's draw out some kind of a diagram that describes what we're seeing, what we're doing a problem with. And let's look at all the tools we have for using what we know to find what we want to know. And then let's put it together and complete the problem. Solve the problem. Any other questions? A negative answer for time? No. Shouldn't get a negative answer. So in the course of solving this problem, you end up with a negative 9.8 in the equation here. But when you add that to both sides, it becomes positive. So you end up with 2 times a positive number equaling 1/2 times 9.8, both positive numbers, times t. So you should end up with a positive number. Where did your negative sign come from? Do you know? The sine function should give you a positive number if your angle is between 0 and 90 degrees, 0 and 180 degrees, in fact. What's your angle? And the sine of 29.8 did not give you is your calculator set to degrees or radians? Yeah, if it's in radians, then that will give you a wrong answer. What is your question? Number 6, okay. Take a look at number 6. Okay, so this by far is the question that most students struggle with in this chapter. How many questions did I put on this assignment? 22. I did actually accidentally include 3 questions involving force, and those were meant to go into chapter 5. So I actually removed them from this assignment. So only 19 questions now, is that what it is? Okay. Well, that's reasonable, I think. Eventually, I'm going to move some of these questions and make them parts of quizzes, I think. But like these multiple choice questions, I'm going to turn into quizzes eventually, but for now, they're in the homework.
Yeah, seems easy enough.
Okay. So problem 6 is the car going off the table, right? I wouldn't say that this is the hardest question, but I think this is the question that most students struggle with in this chapter. It turns out that it's actually, I think what it is that it has so many parts and people are just aren't sure how to do. They're just not, I think it intimidates them more than anything. But this really is no different than the previous questions that we've done. It's just different starting points, different ending points. The thing that is, I think, very difficult for students is to realize that the math will take care of these things. The math will take care of the problem. Those kinematic equations, they can solve these problems. You just have to trust that they can, and you have to get all of the information written down so that you know what to plug in where. That is, I think, the key to these problems that most students struggle with is writing down all of the information and putting it in the correct place. So they've already drawn the picture for you, which is quite nice. And one other thing is sometimes these problems that have multiple parts, students try to treat them like one problem, when really you should treat each individual part as a new problem so that you're not trying to do too much. At the beginning, this car is just going to go from one end of the table to the other end of the table. That's all it's going to do. It's not going off the table at all in part 1, part A. So we have a wind-up car. It's placed on the table. It's released. It accelerates across the table in 1.77 seconds. Find the acceleration of the car. And they've given us an initial velocity. They've given us a distance, and they've given us a time. There is a kinematic equation that will tell you the acceleration. Right?
I was and I wonder how when I was doing it, I was doing something with the wrong calculation because every time I thought I had the right equation, I put it in, I wrong answer.
So this is all in one dimension. So we're only going to be dealing with X, right? So let's write down what we know. And I like to write, I don't like to just go back in here. Sometimes it's useful to just label these like with T, but what I would do is I would actually write everything down. So I'm going to go through and I've got T equals 1.77 seconds. So I know what T is. T equals whatever it is, right? Then I use the diagram. So I know that V0 equals whatever it is. It's 0 in this case. And then they've also told me that the distance, well, in the single dimension of X, the distance is the displacement. So that's X final minus X initial is 2 meters, right? So I write down those things. Those are the things I know. And then I go and find an equation. It turns out it's actually the same equation we used in the past two examples that is going to be useful, because the equation in the past two examples tells us that, and you could actually rewrite this. I would actually rewrite this change in distance, or the change in position to two different positions. I would say, I'm going to start this. This is going to be my starting point, and I'm going to call this x equals 0. That means my ending point, I'm going to call x equals 2. So that this is x initial, x naught, and this is x final, because that's going to make it easier to plug into the equation. But the equation says that x final equals x initial plus velocity initial times time plus 1/2 a times t squared. And we know the time, we know the velocity initial, we know the initial position and the final position. We can plug in all those numbers, and this is t squared, by the way. We can plug in all those numbers and solve for a, and we're done. That gives us the acceleration, right? So that's part A. Did you have any problems with a particular part, or just the whole thing?
Well, no, yeah, that's just like, I don't know, like kept plugging it in, and I must have done something, wrong. Because every time I tried to, the answer and it was wrong, and part A,
So you're just thinking that if part A, yeah, and that's true in these things. If part A is wrong and you're using the answer from part A, the time that you get, or no, the acceleration that you get in part A, then you'll be in trouble. Now, the important thing to remember is that this acceleration that you've just calculated from part A is actually the acceleration in x. But once it goes off the end of the table, that's no longer going to accelerate in x. So the acceleration in x, when it gets off the end of the table, is actually 0 once it flies off the end of the table. So you can't actually use this number in anything else except for part B, because in part B it says, once it reaches the end of the table, how fast will it be going? So you can use it in part B, but after that, it will have no acceleration in the x direction. So now that you know the acceleration in x from part A, can you calculate the velocity final in x once it reaches the end of the table? Yeah, there's an equation that looks like this. Velocity final in x equals velocity initial in x plus acceleration times time. And you know all of those things except for the velocity final. The velocity initial is 0. The acceleration you just calculated right here, and the time is given. So then you can calculate the velocity. That's fine. Once you have that, then you're essentially starting a new problem, because the car accelerating on the top of the table is one problem. But once you get to part C, it's a different problem. Once you get to part C, you're taking that initial velocity, that final velocity in x becomes your initial velocity in x, and now the car is going to go flying off the table. Now, here they're saying we're not going to let it just go off parallel to the table. We're going to put a little ramp on it and make it go off at an angle. So then what you have from part B is actually your velocity vector up this way, but you're going to break that into two velocity vectors, an x component and a y component. And then you'll do two different kinematic problems from there on out. You're getting an answer and it's still not giving you a correct answer.
So technically, because of x being 0, and y and velocity,
Yeah, these first two terms are going to be 0 in this equation. And you're going to end up with just x, which is your 2 meters, right? Equaling 1/2 at squared. And you know what t is. So you're going to divide by t squared on both sides, right? And you multiply by 2 on both sides. So your acceleration should be 2 times the length of your table divided by the time squared. Yep.
So I have.
2 times 1.9 for you, so that would be 3.8. What's your time?
So wait, so I'm taking, that must be why, so I'm 1.9 times 2.
Yeah, because your length of your table is 1.9. You have to put it in, mine was 2 meters, yours is 1.9.
Okay, so it'd be 3, so it'd take 3.2 divided by.
3.8. 2.8.
3.3, divided by t squared, which is 1.66.
Yeah, so you're taking 3.8 divided by 1.66. You're good.
See, I keep getting this answer, which is apparently wrong, unless it's wanting me different significant figures.
That could be the case. I can check that. So you have 3.8 divided by 1.66.
Yeah, that's what I'm.
So you're getting an answer of 2.28.
I'm not getting that, because what 1.6 is 1.66 squared.
Oh, right. 3.8
Divided by 1.66 squared.
divided by. So you're getting 1.379.
Yes, and
And you plugged in as 1.38.
yes, and I don't.
I've noticed that you can't round it off because then it becomes wrong. So there's like no rounding.
1.379. Have you tried just plugging 1.379?
I'm gonna try that. 1.37. Nope.
Okay, well, go ahead. What I'll do is I'll check and see if there's a glitch in the code really quick that's giving you a goofy thing, and then I'll get back to you on that. I have to look at your homework specifically to see what's going on with that.
Okay.
Does anybody else have any? Yours is not coming out right? Let me just check to see if that code is working properly. Remind me of your last name. Carm, Cartmill, okay. So this is homework number 4. No, that's the wrong one. Homework 4. Here we go. So homework 4, number 6, you said? This was number 6, right? Whoa. Yeah, actually, it looks like it is giving a weird answer from the code. Your acceleration, did it come out as 2.29 from in part A? Oh, wait, we're not doing, which, this is part number 6 we're doing, right?
Wait, what did you get when you didn't have the square?
So right now, is that?
I'm wondering if it didn't take times squared, because when you just did that one, you got that answer.
But this is the calculation for the
Yeah, the
velocity.
wrong. Yeah.
So what I'm gonna do is I'm gonna look at the code really quick and see what it's doing.
So we did everything, and then just instead of dividing by 1.66 squared, you just do 1.66, and that's the answer you got. So I'm wondering if it just didn't do it divided by time, just divided by time and not time squared.
X over T. It looks like they actually are, it looks like they actually do have the wrong code, because it should be 2 times X over T squared. Right?
Yeah.
And here they have it as X over T. And then the answer for the second one should be 2 times X over T for the time, right? For the velocity rather. And they showing it as just 2 times X. So that is definitely wrong. I don't think I've ever had that problem go wrong for me before. So I don't know why it's wrong now, because the code used to work. So maybe somebody changed the code. That's really weird. So what I'm going to do is I'm going to change the code just for me. And I'm going to divide this by t squared. And then I'm going to divide this other one by t by get the code. I have to get the way they code it correct. And that 2 times x sine, 2 times x cosine. This should also be divided by t. Should also be divided by t.
On,
Copy. Paste. Paste.
Because when horizontal thing,
Y squared. Let's see, what's the last thing here? Displacement. So this one actually is displacement.
I accidentally just checked. No, that's not true.
I think that one might be correct. Okay, so let's see, number 6, yeah, look for your daily. So be done. Use for third block.
Yeah, I was so upset. I had 4 hours to do all my. I was at like, yeah, we were like, I was at that point, 3 hours straight.
Okay, so I've redone the code and I'm going to check to see if your problem is correct at this point. Your problem is correct at this point. Your acceleration is correct now. Your final velocity is correct now. If you write it out to 2 decimal, if you do 3 decimal places on the first one, it should be fine. If you do 2 decimal places on the second one, it should be fine. And I will change the scores on those so that you're not losing points. But
I also had a question
that should be
about
correct now.
number 4.
The question about number 4, okay.
Because I'm wondering if maybe changes because the technique is different from number 3 and number 3. I did get right. I did get right, but number 4 I get wrong. So I wonder if maybe something about it changing the factor how to get the vertical and horizontal points. Because it said rather than starting at 0, it's starting at, you know, 2 years old.
Um,
Still finding the horizontal, the initial velocity times cosine of.
yes. Your answers are off a fair bit, but let's go ahead and look at that problem separately. We'll talk about how to do that. No, I'm going to go ahead and do it on the screen here. We're actually out of time for the class. So if any of you need to go, if anyone needs to take off or disconnect, you can, but I'm going to continue recording this so that you can see what we're going to do next. And the reason that I wasn't sharing my screen is because I was looking at one particular student's homework, and I'm going to go ahead and look at the general homework assignment so that we can all look at it together. So if you need to go, you can, and you can come back and watch the video of this next problem, which was number 4, you said?
Yes.
So number 4, and this is actually another similar problem, but this one is more complex because we're having different starting heights and ending heights of things. And so that does change things as far as the numbers you plug in, but it doesn't change anything about how you use the equations. So let's go ahead and draw a picture of this really quick. We have a basketball player shooting shots. And we have the first one, the thing that we're going to look at is the ball leaves her hands 13 meters horizontally away from the basketball hoop. And so we have a distance in X. We'll call this X0 will be equal to 0 where she's starting, and where the basketball hoops will be X final, and that will be 13 meters. So this is a deep 3. It's like a half court shot. Anyway, 2.4 meters vertically from the ground would be the initial Y direction height, right? So this Y initial here is going to be 2.4 meters. She's also obviously quite tall. And then let's see. So what they're telling us is that they've given us the velocity vector is equal to 12 meters per second, and the angle theta is 66.3. I don't think she's going to make it. I could be wrong, but we'll see. So 12 meters per second, an angle of 66.3 degrees. We want to find the horizontal and vertical components. Now, did you have any trouble doing that part?
Well, yeah, that's the part I'm
Okay.
because that's the part I have to stop on. Once I get those.
Okay. So this is our vector V. We have our angle theta. Horizontal component is this one, so that's going to be V cosine theta. And then the vertical component will be this one, and that one will be V sine theta, right?
Okay. Maybe problem of counting this.
I'm sorry, what's that?
I did that, that's why I got, for my answer, well, actually, it's 12.
So what are you have 12 meters per second for your velocity?
Yeah, and times my angle is 62. So it'll be times the cosine.
Oh, my calculator's all messed up. Hold on.
Unless maybe that's I'm gonna figure it out. Yeah, I got 5.6. 5.6336.
So 12 times cosine, what's your angle again? 62. Dang it, I'm still in gradients. Why am I still in radians? Oh, not in radians. I'm not in gradients. That's weird. Okay, so enter. There we go. Okay, there we go. 62, 12 times the cosine of 62, which should be about 6 or something like this. 5.6. So did you get 5.63?
I got 5.63. It's counting. 5.63.
Okay, let me check something really quick.
I was gonna say, I'm kind of having trouble with this one too, because I did the same method with on the last problem, but it's just not giving me anything. So I wasn't sure if the spot where the ball left, like, was shot from, so like the 2.4 meters, if that had anything to do with it.
This is. Um, 12 sine 6.3. Okay, I see what they did wrong in the code. They mixed. Oh, no, they actually did the code right. Their code is correct. We read something wrong in the problem. It says right here that the 66.3 degrees is respect to the vertical. So the angle that they gave us was this angle. That's the angle they gave us. Our theta needs to be 90 minus 66.3. Right? So that's
Okay.
that's the only error there.
Yeah, I read the with respect to, and I kept like missing, like,
Yeah.
part of
Well,
me thought, yeah.
that also
Okay.
that also makes more sense basketball wise. If you're going to make that shot with that velocity at 66.3s from half court, you're going to have trouble. So maybe not. I don't know. Hard to say. 12 meters per second is like 25 miles an hour. So. All right. What they don't tell you is the height of the hoop. Should be about 3 meters, the height of the hoop. But they don't actually they're not actually telling you that they're actually going to hit basket. So. All right.
Could you explain number 14 real fast too?
Yeah. And if you send me questions through my open math, I will answer them as well. Is anybody going to need more time on this assignment?
Maybe a little.
Like maybe tomorrow night?
Tomorrow night, probably, yeah. I'd be all right with that.
I mean, we could do a couple of nights if you want, but I try not to make homework due on Sunday because I try to give everybody at least one day off a weekend, but I'll move it to tomorrow night. And if well, that sucks. But we're going to look at question 14 really quick here and see what that's all about.
I think I'm gonna go now.
Okay.
So,
Yep.
you have a good weekend.
Thank you. You too. The proton in a synchrotron is moving in a circle of radius 1 kilometer, increasing its speed by velocity equals c1 plus c2 t squared. So they've given you the numbers to plug into this. So this essentially is a problem where they've given us the function for the velocity. My function looks like this. It looks like 5.9 times 10 to the 5th plus 10 to the 5th t squared. And so if you plug in a time, if you plug in t equals 3 seconds, this equation will tell you what the velocity is. If you plug in t equals 4 seconds, it'll tell you a different velocity. So this is always telling you how fast this thing is moving at different times, essentially. And they want to know what's the proton's total acceleration at t equals 5 seconds. Well, this equation is telling you how fast it's going along the edge of the circle. So if you take the derivative of this equation in time, it will tell you the speed of it along the edge of the circle. It'll tell you the acceleration of it, rather, along the edge of the circle. So if we take the time derivative of this equation, the first term has no time in it. So it's just the time derivative of a constant, which is equal to 0. And then the second term is times 10 to the 5th t squared. And when we do the time derivative of that, we get 2 times 10 to the 5th, because the 2 that's up here comes down in front. And then times t to the 2 minus 1, which is t to the 1. So your acceleration in time looks like this: 2 times 10 to the 5th t. So that tells you the acceleration at any given time. And you're going to need both of these equations to do this problem, because the total acceleration total is equal to, and this equation is in the book in the circular motion section towards the end. The total acceleration is the centripetal acceleration plus the tangential acceleration. And the centripetal acceleration you're going to get by using this equation and calculating the velocity at the particular time, which is 5 seconds. And then you're gonna use the centripetal acceleration equation, which looks like this: centripetal acceleration equals v squared over r. So you'll take the v at 5, and then you'll square that and divide it by the radius of the circle. And then the tangential acceleration you'll get by plugging time equals 5 into this equation, and that'll give you your tangential acceleration. So this is an acceleration total. So this equation ends up looking like this. You plug in 5 into this equation up here, you're going to get a number out. So it ends up looking like v at 5. Whatever number you get out of that, you're going to square it, and you're going to divide it by the radius. And they do an example of this in the circular motion section as well towards the end. And then you're going to add to that your acceleration at 5, and that will give you your total acceleration. And the acceleration at 5 comes from this equation here. So you plug 5 into this, that'll give you this part. You plug 5 into this equation, that'll give you that part. And then you add them up and get a number.
Sounds good. And then for the second part, we're using the speed of light, right?
Yeah, so in the second part, you're going to use this equation up here, and you're going to set it equal to the speed of light, which is 2.99 times 10 to the 8.
Okay.
And that's when it becomes unphysical, because particles with mass cannot go faster than the speed of light.
Okay. That sounds good.
Right.
Perfect. Thank you.
You're welcome.
Have a good weekend.
More questions, Coco? Cameron? I just called you Coco. People call you by your last name much? Really? Oh yeah, that's cool. Cool to have a nickname.